Alright, welcome back. We're going to look at dilutions today. Almost always in the lab we have a solution that is too concentrated for use. And we normally buy the more concentrated solutions because they are cheaper to buy, and we just dilute them by essentially adding water to it to prepare the one we want to. Otherwise we have to pay for shipping all that water to us, and it's a lot easier, just like orange juice, to buy it concentrated and add water than to buy it pre-diluted. There is a really cool equation that we find very useful to use when we deal with dilutions. It's called the dilution equation, and it looks something like this: M1V1 equals M2V2. And the 1s and the 2s stand for before and after. Some people write I and F for initial and final. And what M1 means, it's the initial concentration. And what V1 is the initial volume. And after you add the water, then M2 is the final new concentration, and V2 is the final volume. Okay, and before we go into why this works, let me just go ahead and explain what exactly we are doing here. So imagine you start off with a solution, and we call it a stock solution, mainly because we have it in stock in our stock room, and it's quite concentrated, so it's got a concentration of M1. Okay, now here's the kicker. That stock solution, in order to dilute, what we're going to do is we're going to transfer some of it to another vessel. So we probably wouldn't use a beaker, but we'd probably use something like a volumetric flask or a cylinder or something like that. And so we're going to take some out. So we're going to take some of this out, and it's going to have a volume at this point, V1. Okay, so this is the initial concentration, this is the initial volume. But remember, V1 is the amount you dilute. So even though you might have a gallon of the stuff, if you only take out, say, 1 milliliter, that's the V1 you use. Okay, that's a common mistake, by the way. All right, now we're going to go ahead and we're going to add some water. So we're going to go ahead and we're going to take this, and we're going to add water, and we're going to bring it up to a new volume. So we're going to go ahead and add water and to dilute it. And the final volume now is going to be V2. And the question is, right, presumably we've added water, so it's not as concentrated as before. What is the new concentration? So this is the name of the game, right? So we take our stock solution, we transfer out V1 of it, okay, and we have now the initial concentration and the initial volume. Remember, concentration is intensive, so it's got the same concentration whether we got a gallon or a milliliter. And then we add water to bring it up to a new volume, V2, and now it's got a new concentration, M2. All right, so let's go ahead and move this up and use this in a problem. So for example, perhaps we have concentrated hydrochloric acid, which is 12 molar. And we have a big bottle of it, maybe a gallon bottle, and we take just 2 milliliters of this solution, and we add it to a volumetric flask. So we add it to, say, a 25 milliliter volumetric flask. Okay, and then we add water, pure water, until the total volume is 25 mil. So until it's brought to volume. And the question is, right, what is the new concentration? So how is it in terms of concentration now? So let's go ahead and bring this up and have a look and see what we're doing. So we are taking essentially a volumetric flask. It's going to look something like that. It's got a single mark on, that is 25 mils. Okay, and we are transferring in 2 milliliters of hydrochloric acid. So we've got 2 milliliters of 12 molar HCl, and we've poured it in here first, and then secondly we are adding water second until it's at that total volume. So let's identify the parameters here. So V1 is the initial volume. That's the amount of acid that we dilute. It's not the total amount of acid in the bottle, it's the total amount of acid that we have taken and extracted, and we're going to add water to. The 12 molar, that is the original concentration of the acid we've taken. Okay, now 25 milliliters is our final volume. Okay, and the question is, what is our new concentration? So that is M2. So now we can use the dilution equation to solve. So M1V1 is equal to M2V2. And again, we know this and this and this, and we're trying to solve for this. So what we can do is divide both sides by V2. And if we divide both sides by V2, we're left with M2 all by its lonesome self. So M2 is what we want. And it is M1 V1 over V2. So we can plug these in here. So M1 is 12 molar. Remember, the M stands for moles per liter. The V1 was the initial volume that we had. That was the 2 milliliters. And the V2 is the final volume that we brought the solution up to. That's our 25 milliliters. And the thing to remember here is the milliliters on the top and bottom cancel out. So we end up with units of moles per liter. So if we grab a calculator and we punch it in, 12 times 2 over 25.00, we get 0.96. I'm sorry, I just kind of lost control there. So we get 0.96. All right, should be three significant figures, so it's 0.960, and the units are moles per liter. So that's how we've done the problem there. All right, let's do another example dilution calculation here. For instance, maybe we've got some sulfuric acid. It's 18 molar in concentrated form. And we take, say, maybe 3.5 milliliters of it, and we add... what should we add? 17.5 milliliters of water. And then the question is, what's the new concentration? So what is, and remember, we can write in square brackets whenever we want the molar concentration. What is the new concentration? So this is a dilution, right? We're essentially adding water to it, and that's going to dilute it. So now that sulfuric acid, it's spread out to a much bigger volume. So we can use the dilution equation, right? So M1V1 equals M2V2. We just need to associate everything here. So 18 molar, that is the acid we start with. That's its initial concentration. We're taking 3.5 milliliters and adding water to it. So that's our initial volume we're diluting. So remember, we don't use the volume of the bottle itself, just the volume of what we take out to dilute. 17.5 milliliters is not V2. In fact, we're not actually told V2 in this problem here, are we? So we don't really have V2, but it's very common to assume that the volumes are additive. So we are going to assume that V2 is probably the 3.5 plus the 17.5. So that gives us, to two decimal places, it gives us 21.00 milliliters. And that is an assumption, because it turns out that sulfuric acid and water, they don't mix neatly. The volumes actually are not additive in general, but we can normally say, unless we are told otherwise, we will assume the volumes add up. In high precision work, we wouldn't do this. So that is our V2. So our V2 is our 21 milliliters. So at this point here, if we check what we have here, we've got M1, we got V1, we got V2. We're trying to find M2, so hunky-dory. We can divide both sides by V2, and that cancels out the V2 on the right and leaves us with M2 equal M1 times by V1 over V2. And we can plug these in here now. So M1 is our 18 moles per liter. Oops. Our V1 was our 3.5 milliliters, what we started with. And our V2, with our assumption that the volumes are additive, is 21 milliliters. Sometimes people convert their volumes to liters, and that is totally fine. You can convert 3.5 milliliters to liters by dividing by 1,000. You can convert 21 milliliters to liters by dividing by 1,000. But if you divide the top and the bottom by 1,000, at the end of the day, it all just cancels out. So I would say, why bother making extra work when you can just go ahead and leave it in milliliters? You won't get it wrong leaving it in liters, but you just waste time. So the calculation... my calculator gives me 3, and of course the rules of significant figures would say that in actual fact it should have 3 significant figures, so it would be more appropriate to write 3.00 molar. And remember, that just means that there are 3 moles in every liter of that solution. Now of course we don't have a whole liter at this point, but that can be used as a conversion factor. Now you might be wondering, why does this work? And well, let me explain on the next slide. So our friend, the dilution equation, is M1V1 equals M2V2. And the question is, why does it work? And the reason it works, actually, is that if you take the molar concentration by the volume, that actually gives you the number of moles of solute. And the M2 times V2 also gives you the number of moles of solute. And so if the solute we can represent as little red dots, maybe. Okay, clearly, right, that can't change as we add water. So in a concentrated solution, right? Maybe we have 1, 2, 3, 4 dots there, and we maybe have 4 particles of solute. And as we add water to it and dilute it, so we bring it up to a higher volume, we still have those 4 dots of solute in. They're just more spread out. So we would say before, right, it's pretty concentrated. Afterwards, it's dilute, but it still contains the same amount of solute in. So that's why it works. Now, I said earlier, right, that you can use your volume in milliliters or liters or gallons or hogsheads or whatever you want to. Well, technically at that point there, it's not equal to the number of moles, but it's proportional to the number of moles. And as long as you use the same unit for volume, you can use fluid ounces or gallons here and everything will be hunky-dory. So, very good.